When we sleep, we can't tell the difference between reality and a dream. So how do we know what's real and what's not? To scientists, something is real if its properties are known before it is measured. Even when no one is looking, an apple can be green. However, the quantum world appears to operate under a different set of rules. And 3 scientists were recently awarded the Nobel Prize for proving that our universe is not locally real. But what is this place we live in if our world isn't real? In this video, we'll find out why physicists believe that the universe isn't real. One of the more disturbing discoveries in the last half-century has been that the universe is not locally real. Real in this context means that objects have definite properties that are independent of observation. For example, an apple can be red even when no one is looking. Local means that objects can only be influenced by their surroundings, and that no influence can travel faster than the speed of light. Quantum physics researchers have discovered that these things cannot both be true. Instead, evidence suggests that objects are not solely influenced by their surroundings, and that they may lack definite properties prior to measurement. This, of course, contradicts our everyday experiences. Do you really believe the moon isn't there when you're not looking at it? Albert Einstein once bemoaned to a friend, to adapt a phrase from author Douglas Adams, "The demise of local realism has made a lot of people very angry and has been widely regarded as a bad move." The accomplishment has now been attributed to 3 physicists, John Clauser, Alain Aspect, and Anton Zeilinger. They were awarded the Nobel Prize in Physics in 2022 in equal parts for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Colleagues agreed that the trio deserved this punishment for appending reality as we know it. It had been a long time coming. Sandu Popescu, a quantum physicist at the University of Bristol in England, says, "There is no doubt that the award is well-deserved. The experiments, beginning with Clauser's early one and continuing on, show that this stuff isn't just philosophical, it's real and potentially useful, like other real things," says Charles Bennett, an eminent IBM quantum researcher. "Every year, I thought, oh, maybe this is the year," says David Kaiser, a physicist and historian at MIT. This year it really was. It was both emotional and thrilling. It was a long road from the periphery to the mainstream. From about 1940 to 1990, studies of so-called quantum foundations were frequently dismissed as philosophy at best and crackpottery at worst. Many scientific journals refused to publish papers on the subject, and academic positions devoted to such research were scarce. Popescu's advisor advised him against pursuing a PhD in the subject in 1985. He said, "Look, if you do that, you will have fun for 5 years, and then you will be jobless." Popescu says, "Today, quantum information science is one of the most active subfields of physics. It connects Einstein's general theory of relativity to quantum mechanics by utilizing the still enigmatic behavior of black holes. It governs the design and operation of quantum sensors, which are increasingly being used to investigate phenomena ranging from earthquakes to dark matter. It also clarifies the often perplexing nature of quantum entanglement, a phenomenon central to modern materials science and at the heart of quantum computing." What exactly makes a quantum computer a quantum computer? Mikkel Junger-Halpern, a physicist at the National Institute of Standards and Technology, asks rhetorically. One of the most popular answers is entanglement, and the main reason we understand entanglement is the great work done by Bell and these Nobel Prize winners. We probably wouldn't be able to build quantum computers without that understanding of entanglement. The problem with quantum mechanics was never that it made incorrect predictions. Rather, the theory described the microscopic world admirably from the beginning, when physicists devised it in the early decades of the 20th century. What Einstein, Boris Podolsky, and Nathan Rosen objected to in their seminal 1935 paper was the theory's unsettling implications for reality. Their research, known by the initials EPR, focused on a thought experiment designed to demonstrate the absurdity of quantum mechanics. The goal was to demonstrate how, under certain conditions, the theory can fail, or at the very least produce nonsensical results that contradict our deepest assumptions about reality. A simplified and modernized version of EPR is as follows. Pairs of particles are sent off in different directions from a common source, targeted for 2 observers, Alice and Bob, each stationed at opposite ends of the solar system. According to quantum mechanics, it is impossible to know the spin, a quantum property of individual particles, prior to measurement. When Alice measures one of her particles, she discovers that its spin is either up or down. Her results are random, but when she compares them, she immediately realizes that Bob's corresponding particle, which had a random indefinite spin, must now be down. At first glance, This does not appear to be unusual. Perhaps the particles are analogous to a pair of socks. If Alice gets the right sock, Bob must get the left. But, according to quantum mechanics, particles are not like socks, and they only settle on an up or down spin when measured. This is the central problem with EPR. If Alice's particles lack spin until measured, how do they know what Bob's particles will do as they fly out of the solar system in the opposite direction? Every time Alice takes a measurement, she questions her particle about what Bob will get if he flips a coin, up or down. The chances of correctly predicting this even 200 times in a row are 1 in 1060, which is more than the number of atoms in the solar system. Despite the billions of kilometers between the particle pairs, quantum mechanics says Alice's particles can continue to predict correctly, as if they were telepathically connected to Bob's particles. EPR was designed to demonstrate the inadequacy of quantum mechanics, but instead produced experimental results that reinforce the theory's most mind-boggling tenets. Nature, according to quantum mechanics, is not locally real. Particles may lack properties such as spin up or spin down prior to measurement, and they appear to communicate with one another regardless of distance. Skeptical physicists propose that this puzzle could be explained by hidden variables, factors that existed in some imperceptible level of reality beneath the subatomic realm and contained information about a particle's future state. They hoped that hidden variable theories would allow nature to reclaim the local realism that quantum mechanics had denied it. One would have thought that Einstein, Podolsky, and Rosen's arguments would have sparked a revolution at that point, and everyone would have started working on hidden variables, Popescu says. However, Einstein's attack on quantum mechanics was not well received by physicists, who generally accepted quantum mechanics as is. This was less of a thoughtful acceptance of non-local reality and more of a desire not to think too hard, a head-in-the-sand sentiment later summed up by American physicist N. David Merman as a demand to shut up and calculate. The lack of interest was fueled in part by the fact that John von Neumann, a highly regarded scientist, published a mathematical proof ruling out hidden variable theories in 1932. Von Neumann's proof, it should be noted, was refuted only 3 years later by a young female mathematician, Great Hermann, but no one seemed to notice at the time. Bell's solution to the problem of non-local realism would take another 3 decades. From the start of his career, Bell was bothered by quantum orthodoxy and sympathetic toward hidden variable theories. In 1952, he became inspired after learning that American physicist David Bohm had developed a viable non-local hidden variable interpretation of quantum mechanics, which von Neumann had claimed was impossible. As a side project to his job as a particle physicist at CERN near Geneva, Bell mulled the ideas for years. He discovered the same flaws in von Neumann's argument that Hermann had discovered in 1964. Then, in a triumph of rigorous reasoning, Bell devised a theorem that dragged the issue of local hidden variables out of its metaphysical quagmire and onto the concrete ground of experiment. Local hidden variable theories and quantum mechanics typically predict indistinguishable experimental results. What Bell discovered is that, under certain conditions, an empirical discrepancy between the two can emerge. Alice and Bob received the same paired particles in the eponymous Bell test, but now they each have 2 different detector settings, A and A, B and B. These detector settings are another ruse to deflect Alice and Bob's apparent telepathy. One particle cannot know which question the other particle is being asked in local hidden variable theories. And with that being said, it's time to end our video. Subscribe to the channel for more amazing videos like this. We'll see you with another interesting video.